I'm welcoming you to the lecture A05, where we'll look at equilibrium of a rigid body. If you can remember, in lecture A2, we looked at equilibrium of a particle, and that was on 2 dimensions. But today, I would want to teach you on how to solve problems concerning equilibrium in, of course, the first simple way of your understanding is by going through problems that are in 2 dimensions before you go to 3 dimensions. I stated some time back that 2D, these are just imaginary concepts that we normally put to help the students to understand. Real problems are always in 3 dimensions. Then, the same lecture, that was lecture A2, I tried to introduce you to a free body diagram, but now that one was just concerning a particle. This time you look at real problems that will be in 3 dimensions. Then also, I'll further teach you on how reactions at support and connections are supposed to be used. As an example, a roller. As an example, a pin connection. What type of reactions do you have there? That is, of course, both. We start with a simple way, the simple explanations that will be 2 dimensions. Then we deal with actual engineering problems that are in 3 dimensions. And before I close this lecture, that is lecture A5, I would want you to appreciate how members behave. When you are designing a structure, you need to understand the terms that are normally used, like statically indeterminate reactions. These terminologies will be used mostly in advanced courses in 3rd year, 4th year, and 5th year. The lecture objectives: to study the equations of equilibrium for a rigid body, to introduce the concepts of a free body diagram for a rigid body, to show how to solve rigid body equilibrium problems using the equations of equilibrium. Here, the drawing to my left is just showing you this is some sort of a crane where you have a load which is being supported by this system, which is a crane. And where this crane is located is supposed to be in a river. This is supposed to be a river, maybe a ocean. The crane has been positioned in a situation, or rather in a manner, that the load that is being lifted and the loads that are supporting the crane itself are making the whole system to be in equilibrium. Meaning, there is a load here. We can call it W. We can call that W. And at the same time, we have supports for the crane. What this simply means is the hydraulic loads that have been exerted to the ship and the load W are working in a manner that the crane cannot fail. That is by maybe rotating either in that manner or in that manner. The introduction. Statics deals primarily with the description of the force condition necessary and sufficient to maintain the equilibrium of engineering structures. This lecture on equilibrium therefore constitutes the most important part of statics, and the procedures developed here form the basis for solving problems in both statics and dynamics. Each and every infrastructure, each and every building that you have seen, it is standing in equilibrium. That is the basic or the major principle of structural engineers. You have to make sure that buildings, members, structures do not fail, do not collapse, just by applying the equations of equilibrium. These are summation of forces, whether in 2D or in 3D, that is in the X, Y, and X axis. When you do the summation of those forces, they're supposed to be equal to 0. This also applies for moments. Summation of moments about a specific point should be equal to 0. Can you remember the R cross F? This is the cross product. This is the tool that we use to calculate the moment of a force about a point in 3 dimensions. But in 2 dimensions, we normally use a simpler way, which is a scalar analysis, where we just multiply the force times the perpendicular distance. We will continue use of the concepts developed in previous lecture notes involving forces, moments, couples, and the resultants as we apply the principles of equilibrium. When a body is in equilibrium, all of us, we need to know that the resultant force is equal to 0. If you can recall, when I was showing you calculating the resultant force using the parallelogram or the polygon method, when you add up those forces, the first and the last, they'll end up closing up, meaning the tail and the tip of the last force will be in contact, meaning the resultant force would be 0. Basically here, I'm just showing you this is a rigid body with some forces, that is F1, F2, F3, and F4. And at the same time, we have got a moment M1 and M2. This is just equivalent to the resultant force and the resultant moment. Since this body is in equilibrium, so the force that has been exerted on this body, F1 up to F4, they are not making this body to rotate or to translate. The body is in equilibrium. So how do you arrive at this body? By applying the basic equations of equilibrium. That is summation of forces in the y, summation of forces in the x, summation of forces in the z. That is if it's in three dimensions. And at the same time, summation of moments. The necessary and sufficient conditions for a static equilibrium of a body are that the resultant force and couple from all external forces form a system equivalent to zero, just as I'm just from explaining. The basic equations are summation of forces in the x, in the y, and in the z to be equals to zero. And this also applies for moments in the x-axis, in the y-axis, and in the z-axis. You can remember this equation from lecture A4, where we can change a rigid body with a number of forces such as F1, F2, F3, F4 into one rigid body, which is going to have the resultant force and the resultant moment. When applying the equations of equilibrium, we will assume that the body retains rigid. In reality, however, all bodies deform when subjected to loads. Now, the assumption made here is the deformation is negligible. The deformation is negligible. So, in statics, that's our assumption. But when you go to the second part of C2219, which is the strength of material, deformation won't be negligible. You will now be calculating the deformation caused by the load. So, for statics, this is the assumption that the bodies remain rigid. Of course, deformation is there, but negligible. And note that all physical bodies are in three dimensions. This I have emphasized several times. But we can treat many of those as two dimensions when the forces to which they are subjected act in a single plane or can be projected onto a single plane. When this simplification is not possible, the problem must be treated as a three-dimensional problem. Take note of that. If you cannot simplify, you can't make that your problem into two dimensions, you have got no any other option but to solve that problem as it is, that is in three dimensions. So, in this lecture, we will first discuss equilibrium of bodies subjected to two dimensions, and the second part will be in 3D. Why is it like that? When we do it in two dimensions, we are just trying to make you develop the tools to apply, it becomes easier to solve problems in 2 dimensions before you start solving problems in 3D. So we'll start with simple problems, simple imaginary things, imaginary problems in 2 dimensions. And of course, those real ones in 3D, but they can easily be translated into 2 dimensions before we start solving problems that are in 3 dimensions. So, equilibrium in 2 dimensions. This is just an example where you can see there's an aeroplane there, right? This, in reality, it is in 3 dimensions. In reality, it is in 3D. It has got the X, Y, and Z axis. But we can solve this type of a problem as a 2D dimensions. How do we do that? When you look at the wheels, except this picture is not showing you the other elevation, maybe viewing it from front. I mean, viewing it from front. You could have seen that the front wheel, there is only one wheel. The rear wheel, there are 2 of them. But instead of analyzing it in 3D, we can solve it in 2D, where we are going to have a reaction as R on the front wheel and T, which is going to be 2T, representing the 2 wheels, which are the rear wheels. This is how we can translate certain problems from 3D to 2D. So, successive application of the equations of equilibrium requires a complete specifications of all the known and unknown external forces that act on the body. For now, we are only looking at the external forces, not internal forces, as I explained in lecture A1 and lecture A2. The best way to account for these forces is to draw what we call a free body diagram. A free body diagram is a sketch of the outlined shape of the body, which represents it as being isolated or free from its surroundings. On this sketch, it is necessary to show all the forces, couple moments that the surroundings exert on the body, so that these effects can be accounted for when the equation of equilibrium are applied. A thorough understanding of how to draw a free body diagram is of primary importance for solving problems in mechanics. So, if you don't understand what a free body diagram is, you can't draw a free body diagram, then you cannot solve problems in engineering mechanics. So, it is necessary for you students to understand what a free body diagram is and how to draw one before you start solving problems in mechanics. Modeling the actions of forces. Before we discuss more about a free body diagram, I think this is the right time for you to understand how our members are being supported and how the reactions are. If you don't understand the supports and the reactions, still, even if you understand the free body diagram, how to draw it, it will be of no benefit, because it is from your understanding of the supports and the reactions that will make you isolate that body and come up with a free body diagram. So, as a general rule, a support prevents the translation of a body in a given direction by exerting a force on the body in the opposite direction. A support prevents the rotation of a body in a given direction by exerting a couple moment on the body in the opposite direction. I'll show what I mean. So, for an example, you consider three ways in which a horizontal member, that is a beam, if you don't understand what a beam is, all of us, we come from I'm sure all of us come from a house, maybe a shelter. In that shelter, it has got some openings, such as a door, a window. So that opening, above that opening, the window, the door, there is what we call a beam, which is being supported by, of course, walls on the ends of maybe the door or the window. So, when you look at this is a beam, this is just not a complete beam. If it's a complete beam, we need to have another force there. If it's a complete beam, then of course this will be the opening space I'm talking about. This is the opening space I'm talking about. So here it is being supported by a roller. What does it mean by a roller? This, it simply means this beam can translate in this direction, that is the horizontal direction, but it cannot translate vertically. Why? Because there is a force preventing the beam from translating in that manner. So these are examples showing you how a roller looks like. You can have that type. This is a roller. This is a roller. This is also a roller. Frictionless surface. Always, the reactions is always a vertical force, which is this. There is no horizontal reaction. This force does not exist. So you really need to understand, because in engineering problems, you would find that certain members, you make an assumption that I'm going to design a beam as a fixed support, or as a pinned support, or as a roller support. Once you make that assumption, then you need to know how to come up with a free body diagram for you to calculate the loads, the moments, the shear force of those members. The beam can be supported in more restrictive manner by using a pin. So here I'm just showing you how a pin looks like. This is showing you it has got a member, which of course can be a beam itself. Then we have got a pin. Then we have got levers, which supports the member. So this is how the pin reaction looks like. So for a pin, always note that this member cannot translate in the vertical and cannot translate in the horizontal manner. That's the reason why the reactions that we have with a pin connection is always F in the X and F in the Y. But this can rotate either this direction or this direction. That is a reason why there is no moment which is preventing the beam to rotate. So the only reaction that we have on a pin support is just those two members. The member itself in the X and the other member in the Y. This is also the same as representing it depending at which angle it is being applied. Can you remember about the components of a force? You have a force at an angle, then you find the components in the X and in the Y. This is exactly what is happening. The most restrictive way to support the beam would be to use a fixed support as shown. A fixed support, this fixed support, it is preventing rotation, translation in the X and in the Y direction. So whenever a beam, whenever a member is being supported by a fixed it's supported by a fixed support, you always consider there is a moment, there is a component in the X and in the Y that is from the force. Take note of that. Wherever is a fixed support, you always need to consider there is a moment, there is a force component in the X, a force component in the Y axis. So these are just examples of types of reactions. The first one, it is showing you that a flexible cable, it can be a belt, it can be a chain or rope. Then we have the first one, which is where the weight is negligible. And the other one, of course, the weight is not negligible. The assumption that you make here is always, if you remember, a rope is always in tension. So this is how you draw your free body diagram. This is how you draw a free body diagram. When it is a smooth surface means this body can still translate in this direction. So there is only one direction where it cannot translate. Why? This is where it is resting. If it was not resting, of course, we would have applied the laws of gravitation. So that is where it is being supported. So the only reaction is the N, which is of course opposite the force, because we know there is also a component, the weight of the body, which is also facing, of course, opposite the reaction. Then when a surface is rough, when it's rough, that body cannot translate in the X or Y direction. So this simply means on your reaction, when you are doing your free body diagram, you need your X and Y. As I mentioned, for a roller support is always one vertical force. For a freely sliding guide, even the word itself says freely sliding. So this body cannot only translate vertically, but it can move left and right. It can move this direction and this direction. It can move that direction. So it is not being prevented. Therefore, when you draw a free body diagram, the only reaction that you need to put there are supposed to be the forces vertically. Then a pin connection, I've already mentioned about the pin connection. A pin connection, if the pin itself, it is being prevented to rotate, then you only consider two forces, which is the one in the X and one in the Y. There's no moment. Why? Because it can rotate. But if the pin is not free to turn or to rotate, then that simply means there is a moment which is preventing that member to rotate. Built-in or fixed support. A fixed support, as I discussed, always we are going to have the force in the horizontal, the force in the vertical, and the moment. Gravitational attraction is always the force direction downwards, because all of us, we know, if you have got an apple, you throw it up, whether you like it or not, it will still come down, which simply means it is using the gravitational law. For spring actions, I won't discuss much about this, because in statics we don't necessarily consider springs, but in these courses coming third year and fourth year, you will learn more about the spring. But here we are just trying to show you on how a spring behaves. So this is the equation that we use, which is the F is equals to the coefficient times the X. The X, that is the distance. The coefficient, that is the coefficient of the spring itself. This also applies for torsional spring. When you look at it, it's already showing you that there is a rotational reaction there. So the only thing that you look at is the angle and that moment. Plus, of course, you need to consider the coefficient of that spring. List of common types of supports for bodies subjected to coplanar force system, showing the types of reaction they exert on their contacting members. Or in all cases, the angle is assumed to be known. Therefore, the list also shows the number of unknown reactions. So here you have got a table which is showing you types of connection, the reaction, number of unknowns. It is very much important for you to know the number of unknowns. If you have more unknowns than your equations, then it will be very difficult for you to solve that problem. So you need to analyze, you need to assess the member and try to analyze the number of unknowns and also the reactions. It's the same table that is just showing you on what normally happens on a roller, what happens on a roller in terms of the reaction, what happens on a smooth surfacing, as I was just explaining. But this is just helping you for you to understand how many unknowns do we have. This is also the same application. This is also a continuation of the same table, showing you the number of unknowns and the reactions. Typical examples of connections and reactions. Those who have been to the Great East Road campus, that bridge, which is just across as you are going to Kalundu, you have seen this type of a rope before. How do you come up with a free body diagram of that? What about this beam, a concrete beam? What about these other beams? When you just look at that, this looks like a roller. When you look at that, this looks like a simply supported a pin connection. How do you come out with those support reactions? Now, we come to how to construct a free body diagram. Note that a free body diagram is the most important single step in the solution of problems in mechanics. If you don't understand the free body diagram, then you won't be able to solve problems in engineering mechanics. The full procedure for drawing a free body diagram, which isolates a body or system, consists of the following steps. Number one, decide which system to isolate. The first thing is you decide which system to isolate. The system chosen should usually involve one or more of the desired unknown quantities. At least you need to have one or more of the desired unknown quantities, but also try to start with the one with the minimum number of unknown quantities. Next, isolate the chosen system by drawing a diagram which represents its complete external boundaries. Forget about the internal members. We are only looking at the external boundaries. This boundary defines the isolation of the system from all other attracting or contacting bodies, which are considered removed. This step is often the most crucial of all. Make certain that you have completely isolated the system before proceeding with the next step. Step 3. Identify all forces which act on the isolated system as applied by the removed contacting and attracting bodies, and represent them in their proper position on the diagram of the isolated system. Here what it means, if you have got forces, show those forces where they have been exerted, the distances, the direction, if it is facing, if you maybe say it's a moment counterclockwise, clockwise, represent them exactly the way they are. Make a systematic transverse of the entire boundary to identify all contact faces. Those contact faces are very much important for you to come out with what type of reactions do you have there. Is it a roller? Is it a pin connection? Is it a fixed connection? And if it's a fixed connection, what type of reaction do I have? Of course, they have got a moment and I've got a force in the X, a force in the Y. That is in 2 dimensions. Represent all known and unknown forces by vector arrows, each with its proper magnitude or unknown magnitude, direction, and sense indicated. I think I mentioned this. If the sense of the vector is also unknown, you must arbitrarily assign a sense. You assume from your judgment, when you look at your free body diagram, you can easily judge to say my force supposed to be facing left or right, up or down. If it's a moment, counterclockwise or clockwise. It is necessary to be consistent with the assigned characteristics of unknown forces throughout all your calculations. you need to be consistent. You need to be consistent in terms of signs. If you have assumed to say that force 1 is facing left, let it be facing left. If you find out, once you do your calculations, you find out that your assumption is wrong by finding the magnitude to be negative, that simply shows that the assumed direction is supposed to be opposite. That's what it means. Step 4. Show the choice of coordinate axes directly on the diagram. This is very much important. If you remember, each and every time I'm giving an example, the first thing that I do, I'm going to assume this is my X and Y. Always. This is very much important. Pertinent dimensions may also be represented for convenience. Note, however, that a free body diagram serves the purpose of focusing attention on the action of the external force, and therefore the diagram should not be cluttered with excessive irrelevant information. Don't make your free body diagram like you are an artist, you are drawing something. No, if you put a lot of things, you end up get confused. So a free body diagram, just put things, items that are necessary. Put the forces that are necessary. Put the dimensions that are necessary. Put the signs, the angles that are necessary. Not everything. So here, this is just an example of a free body diagram. A truss shown as number 1 there. If you want to draw a free body diagram, I don't need the internal members. I don't need anything here. For now, I'm not calculating anything. I'm only looking at the external members, external forces. So I don't need anything inside here. I don't need anything here. Nothing. So what do? I'm just going to draw the boundary, which is this. Once I do that, where do they have external forces? I have got a P, which is the one that I have there. And at the same time, you need to remember the reactions. What type of reaction? When I look at that, that is a pin. So a pin will always have two, one the horizontal and the other one the vertical reaction, which is that represented at the AX and AY. And when I look at B, that is a roller. Always if it's a roller, I know there's only one vertical force, which is being represented as BY. You go to a cantilever beam, that is number 2. You have force 1, force 2, force 3. When I look at this reaction, I know that that is a fixed connection. That is a fixed connection. Well, it's a fixed connection. I need the vertical force or the vertical reaction, the horizontal reaction, and the moment. Apart from that, the member itself, the beam, it has got a mass of m, so I also need to represent its weight, which is being shown there as W is equals to the mass times 9 times 8, 1. Then when we go to the other beam there, when you look at B, what do I have at B? That's a pin connection. A pin connection, I also need the vertical and the horizontal reaction, which is being represented as BY and BX. Of course, I also need the member itself. And let me not also forget the mass of the member. Then at the same time, I've got a moment. And at the same point, I've got a support at A. When you look at it, that is just like a roller. I only need a perpendicular reaction to the member, which is that is being represented by N. Always don't forget about your axis, your X and Y. It's always important. Always important. Let us not forget about the X, our axis. Then again, we have another one, which is a rigid system of interconnected bodies. I don't need anything to do with this. I'm only interested in the roller itself. That's the external reaction. That is a pin, right? And of course, I've got a mass there, which is of course the M. This is a rope. So the tension that I have here is the same as the one that I have here. It's the same as the one that I have there. It's the same as the one that I have there. It's the same as what I have there. So I'm only drawing things that are necessary, because once I get this W, it will be the same as the tension in here, the tension in here, and also the tension in here and here. So you only draw things that are necessary. Example. This example is just showing you on how to draw a free body diagram. Now, when I look at this free body diagram, it's very simple. I don't need anything on these members. These are internal members. For now, I'm only looking at the external members and the reactions. So when I look at A, that is a pin connection. I need one force in the X, one in the Y. And let us forget, always we need to define our axis, which is our X and Y. So that at A, I know I'm going to have one reaction. I can call it FAX, or I can call it AX, and the other one will be AY. Then at B, when I look at B, it is a roller, so I only need a horizontal force, which can be B. Then at the same time, this member, this truss, it has got a mass of 2,400 kgs. So it needs to be represented on our free body diagram, which will be, of course, a 2,400 kgs times 9.81. Am I right? Or maybe that 2,400, no, that 2,400, it is for the weight. That is supposed to the load. Yeah. So you do the same, you multiply that 2,400 times 9.81 and the mass of the member. Then this is how your free body diagram looks like. You only put necessary information, such as the dimensions between the forces.
I think here, from the attempts that you did, let me just try to as well model the reactions on the given free body diagrams that are shown on this slide 27. I think the first one, it's a bell. supporting a mass M with a pin support at A. So we all know that a pin is always, this is 2D, as you can see there, X and Y. So if we say this will be the, if we say that we agree that this is X and this is Y, right? So when I look at the first one, if you remember, I mentioned about two types of methods that you're supposed to use as you are drawing your free body diagram in terms of the sense of the forces, the direction of the forces. So the first one was by inspection, and the second one is by assumption. If you assume, you can put it in any direction, left, right, up, down, right? But by inspection, there are only two forces there. There is the mass, the weight of that mass that you can see, which is that, right? The direction is going downwards. So at A, since it's a pin, it would simply mean I need two reactions, one in the X and one in the Y. So in this case, there is only one force, which is the mg. So if that is the only force that we have, then if you remember the third law, Newton's law of motion, it states that wherever there is a force, you need to have a force of the same magnitude and the opposite to the initial force. So in this case, from inspection in the y-axis, I'm going to have a force in that sense, which will be the Fy. Then again, I go back to T. When you look at T, it's facing to the left. So using again the same principle of Newton's law, you need a force which is equal but opposite to T. So in the Y, in the X, the force will be like that, which will be the Fx. Then you are done with number one, right? The second one, control, then there is a moment, right? So even here is a matter of inspection or assumption, right? Because I don't know the FO and PO, what are they going to create? Because when you look at the FO is facing downwards, P is facing upwards, right? So when you look at FP, it is trying to turn. It is trying to turn in this direction, right? And this one is also trying to rotate in that direction. So my moment, the moment is supposed to be opposite to the reaction that had been created by P. So in this case, by inspection, the moment would be opposite to that, which would be that. That will be your moment, right? This is clear. Let me just try to erase these other stuff so that you can just remain with the moment. We go to the third one. The third one, boom OA of negligible mass compared with mass M. Boom hinged at O and supported by hosting cable at B. For this is just more like a pin. We take it just like a pin, which will be by inspection and of course the other force. The fourth one, using crates of mass leaning against smooth wall and supported on a rough horizontal surface. So now we don't know, but from what I can see, D, that is a rough surface. So when there's a rough surface, which simply means this crate is not allowed to move in the x-axis. So we are going to have another force there, which will be Fx. For number 5, load bracket supported by pin connected at A. Load bracket supported by pin connection at A. So automatically where there is a pin, we know the pin there too, right? So by inspection, I would say the first force in that manner and another force, right? Lone roller is a roller of a mass M being pushed up, inclined at a certain angle theta. Wrong or incomplete free body diagram. Me, I would say it's wrong, right? Because the force mg is supposed to be facing downwards,
according to gravitational law,
right? Pray bar lifting body A having smooth horizontal surface, bar rest on horizontal rough surfaces. Is this wrong or incomplete? For me, when I look at this, I can say it's wrong. Because when you say summation of forces in the Y, you find R is going down, P is going down, N is also going down. There is nothing like that in equilibrium. So this would mean the N is supposed to be facing this manner. Then again, when you look at the P, is being applied at an angle, which will simply mean it's supposed to have a component in the x-axis, right? Here they have said the rough surface. So where it is rough, which is supposed to be this surface. So we're supposed to have we are supposed to have another force facing that direction. Then it becomes complete. Then number 3, uniform pole of mass M being hoisted into position by a winch, horizontal support pertaining surface notched to prevent slipping of pole. So where there is a notch there, it's not supposed to move in the X, right? The MG, right? The R. When you look at a notch to prevent slipping of the pole, so it cannot supposed to slip. It's not supposed to move in the X. It's not supposed to move in the Y, but it can move in the other direction. So even here, you need another force there, which will be Rx, where this is Ry. Supporting angle bracket for frame pin joints. So when you look at it, it's not complete. But if maybe we just look at A, B, yeah, but there is A, B, and F there, right? So if you just want to come up with a free body diagram, and of course to model the reactions of A, B, they have said it's a pin. So when it's a pin, we need another force there. That will be AX, where that is AY, right? Then at the same time, since it's AB, that is also a pin. So here we also need another force in that direction. That will be BY, right? Then this is also can also apply for the other arm, which is that. Here I'm going to have that and that, right? Then here I already have point B, which will be that and that, right? Then here you are going to have F. Then it's complete. The last one, I'm telling you this is the last one. Here we have got a fixed, this is a fixed connection. So on a fixed connection, you need another force and a moment, right? So here we have got a force P facing the left direction. So we need another force there opposite to P. This will be AX. And at the same time, we need to have a moment which will be that moment. Then we are done.
You can even check on my YouTube. You have more of those. Thank you for now. We break, then we'll continue.